Okay. So weather is cold, so take care of yourself. And okay, so in the previous class we learned about the address translation. So another address translation mechanisms. So we learned about the page level address mapping mechanism. So actually in the previous classes, we learned that there are pros and cons for block mapping and page mapping mechanisms. So, and then actually the workload to the storage systems have various aspects. So as you know, the computer systems, the lots of kinds of applications can run under this the high performance computer systems. So the workload characteristic, so that means that the request to the storage system may have a wide range of various characteristics. So usually we can categorize these request to storage devices as the sequential accesses and random accesses. And then that's so actually the our data is stored in the memory devices or storage devices. So that means that so our data can be accessed randomly or sequentially. And then that is also true for the memory devices such as DRAM or also in the cache memories. And then the same characteristics can be applied to the storage devices. And then actually to the operating system regards the storage devices as the block-based memory devices. So sorry, each sector of storage devices are accessed by sector addresses. That is also true for the SSD, because the SSD use the flash memory as their main storage media. Also, we learned about the basic characteristics of flash memory. And then in order to cope with these basic characteristics of the flash memory, the SSD supports the address translation. That is the logical block translation from logical block address to the physical page address. Okay, and then the address translation mechanism, we can categorize the address translation mechanism as the page mapping and the block mapping. So we learned about the hybrid mapping. But actually, so we learned about the hybrid mapping algorithms such as fast and fast. Also, in the previous class, we learned about the page level mapping based mechanisms, such as the DFTL, the demand-based FTL. But as you know, as you can see, the baseline approaches, actually the researchers of these the address translation mechanisms applies the already known approaches to the storage research area. So what does that mean? So actually for the hybrid mapping, we learned about I believe everyone knows about the basic cache structures, such as fully associative cache, set associative cache, or direct mapped cache. So as you know, the page mapping algorithm is similar to the direct mapped cache structure. And the set associated cache is similar to the, so it can be related to the block mapping algorithms. Okay, and then so if you know about some baseline characteristics of these direct map or block map set associated cache structures, then you can easily understand what are pros or what are cons of these page mapping or block mapping approaches. Okay. Also, in the previous class, we learned about the demand-based FTL. And then, as actually the baseline ideas for this FTL is similar to caching. So how can you apply? How can you apply cache? Or why do you need cache? Then what property of applications are applied? So that means that exploited for these caching approaches. Actually, that is simple. So we can, so for the cache architectures, we exploit the locality. Well, that means the temporal locality or spatial locality. So we not to exploit these localities observed in applications, we use cache hierarchies. And then the similar ideas can be applied to the FTL, the page mapping algorithm. So there are nothing new in our research field, so we can apply the past ideas. So it's already known ideas to our some new research areas. Okay. Also, so the hybrid mapping algorithm, hybrid mapping algorithm use the log-based file system. It's actually the similar approaches can be applied to the non-volatile memory systems. Okay, because the right property. So actually, usually the right properties of non-volatile memories are so worse than the reading properties of these non-volatile memories. So we can apply the similar approaches to non-volatile memory accesses, or even to SSD. Okay, so there are nothing new in our research field actually. Okay, so so we learned about, in the previous class, we learned about the demand-based FTL. And then actually the baseline idea for this demand-based FTL is that the frequently used page mapping tables are managed inside of the DRAM cache or DRAM of the or SRAM of the SSD, and then the remaining parts. So that means the page level FTL, page level address mapping table, but this address mapping information is not frequently accessed or frequently used. So this address mapping information is managed inside the flash memory, because the flash memory is the number of the memory, but it's cheaper than DRAM or SRAM. Also, density of the flash memory is denser than it's higher than the density of the SRAM or DRAM. But the main idea is that it's cheap, but the performance is low. So it's a basic caching ideas. Okay. So but in order to reduce the cost for this page level mapping algorithm, so sometimes the DFTL requires the more flash memory accesses, like this worst case cost is case 3 is 2 translation page reads and then 1 translation page write. Okay, so sometimes we need to consider these performance cost for some more cheaper ideas. Okay. Okay. So in this time, I will slightly cover another page level mapping idea. It's called the SFTL. So actually, the ideas for this SFTL is very similar to the ideas in DFTL. So in the SFTL, this FTL use the flash memory space as the main space for this large page mapping table and the DRAM. So DRAM area, DRAM spaces. So this SFTL uses the DRAM space as the cached space for this large page mapping table. But in order to use this DRAM space more efficiently, the SFTL applies some that can be called some compression-based ideas like a bitmap-based sequential or random access marking. So SFTL applies the bitmap-based compression. That can be called the compression ideas. Okay, so using this bitmap-based mapping, the SFTL reduce the required size for the required space for this cached page level mapping table. Okay. So how can we apply this compressed? So actually this paper starts from the existing approaches for this page level address translation in SSD, like the page level FTL or block level FTL. So we already learned about these two different approaches, so page level FTL or block level FTL, and we already know the pros and cons of these approaches. And then SFTL. So actually this SFTL the name of the SFTL comes from the spatial locality aware FTL. So what does that mean? So spatial locality means that, so it's similar to the spatial sorry. It's similar to the spatial locality observed in the normal applications. If the one page is, so that means that a certain address of data is accessed, then with high probability, the neighbor data, that means that the data of adjacent addresses are frequently accessed. That is the property of spatial locality. So that property can be also applied to the storage systems. Actually, the data is also, the same data is stored in the storage system. So that means that the same property can be applied to it is stored data in the storage system. So what does spatial locality in storage system mean? So simply, if the one page is accessed by host systems, then the adjacent pages, that means the neighbor pages, are frequently accessed with high probability. So SFTL exploit this property. Okay. So basic approach of the SFTL means that, so if the one page is accessed, then the neighbor pages are accessed, and then the another neighbor pages can be accessed frequently. It's similar to the sequential accesses to storage devices. And then we already know that in the some workload to the storage devices, then random accesses and sequential accesses are frequently found. Actually, those different access patterns are mixed in our normal workload to storage devices. And then these same properties can be found in our normal applications, and the SFTL exploit this property. So that means that, so if the one page is accessed, that means that the one page is written to the storage system, and then with the high probability, the next pages and then the next pages can be written sequentially. So actually, we know that the all accesses to storage devices are not sequential accesses, but these sequential accesses are frequently found. And then if these sequential accesses are frequently found, then we can selectively apply the compression to these sequential accesses. So that means that if so this is the, so it's called the logical page number in this paper. So and then this is the physical page number. I frequently use the PPA, the physical page address, but the physical page number is also the same meaning. Okay, so these logical page numbers are mapped to the physical page number or physical page addresses. Then these logical page numbers can be sequentially mapped to the physical page numbers. So and then that is frequently observed. So that means that, so if the data is written sequentially to the storage devices, then it's true. So the main idea of this SFTL is that if we just know this base mapping information, and then this address mapping from logical page number to physical page numbers are sequentially mapped inside of SSD, then we can, so it's a 9. So if we just know this mapping information, so 8 is mapped to 1, and then if we know the length of the sequential mapping, so that means that the data is sequentially written to the storage devices, then we can easily know, so 9 can be mapped to the physical page address 2, and then 10 is 3, and then 4 is 11, like this example. Okay, so what does that mean? If we just know the start point of sequentially mapping information, so sequential mapping page translation, and then we know, and then if we know the range of this sequential mapping information, sequential mappings, then we can compress the mapping information. Okay, so in this example, so we can find the sequential mapping from 8 to 11, and then also we can find the sequential mapping from 12 to 15. And then the SFTL marks this sequential mapping with the bitmap based it's not compression, it's a bitmap bitmap based mapping. Okay. So 8 is the start point. So that is the base point of this sequential mapping. So SFTL marks the start point of this sequential mapping as 1. And then the next page is 0, 0, 0. So that means that the bitmap, if the bitmap is this bit number is 1, that means that this is the start point of the sequential mapping. So actually the neighbor pages like 9, 10, 11, we can calculate the mapped physical page number based on the 8, so 1. So 1 plus what's that? It's 9, 8. It's like this. Okay. So basic idea is that this mapping information is cached in the DRAM, but we already know that DRAM is very precious resources in SSD because DRAM is expensive, and also the DRAM spaces can be used for proper space for this SSD. Also, DRAM space can be used for some additional space for some firmware or some. Even if we can apply the in-storage computing, then we can use this DRAM space as this in-storage computing applications. Okay. So in order to reduce the DRAM space for this cached page mapping information, the SFTL used some compression-based mapping. And then this compression-based mapping can be efficient. The fractions of sequential mappings is very high. Okay. So in this paper, so you can find also there are 5, 12 entries, and then each page, each translation, the size of each entry is the 4 byte, and then the assumption is the fully contiguous. So that means that the entirely sequential mapping. So we can reduce the space as the 96, about the 97%. See? But as you know, this is the already known compression approach. So this compression approach can be applied to this SFTL. So it's the main idea of the SFTL. So why? How can you apply this compression approach to this FTL? Because sequential accesses are also frequently found. So we know that the random accesses are also found. It depends on the characteristics of workload. Also, it depends on the characteristics of file systems. But we already know that for some data part, the main data part, the sequential write or sequential accesses are frequently found. So that means we can apply this compression-based page level mapping to the data space in the storage systems. Okay. So actually, the main mapping table is mapping tables are managed inside of the flash memory because the flash memory is cheap. But for the cached pages, so we can apply this bitmap-based compression. So it is because we can. So how can sorry? How can you apply this compression-based structure? Because of the sequential accesses. That means that the spatial localities to the are frequently observed to the page accesses. So ideas are applied, and we can compare the performance of the proposed idea with the previous work. So this paper compares the performance of this SFTL with the FTL and fast and then optimal FTL. This is the page level FTL. And then as you can see, this SFTL exploit the spatial locality. So that means that the sequential accesses to storage devices. So in order to, so in the evaluation part, that means that the researchers need to show the fractions of random write and then sequential write. So as you can see, you can find that the fractions of sequential read and then fractions of sequential write for each workload. Okay, so it's a request size and then percentage of reads are also exhibited in the paper. So hit ratio. So it's also based on the caching idea. So this paper also shows the hit ratio of this SFTL idea. So as we can expect, the SFTL compress the page, the mapping information. Okay, that means that more mapping information, so more mapping tables can be cached in the same DRM space, same size of DRM spaces. Okay, so that means, so actually the test is the hybrid mapping. So the all address, the page mapping tables are managed inside of the DRM. So that means the hit ratio is always 100%. This is the optimal solution. The all page mapping tables are managed inside of DRAM of SSD. It's always 100%, but as you can see, the DFTL, the hit ratio is around so it's lower than 50%, but the hit ratio of the SFTL is higher, much higher than the hit ratio of DFTL. It is because the cached mapping information is compressed. So response time. So we can expect that the page level mapping exhibit higher performance compared to block mapping or hybrid mapping. So the system response, if we just compare the system response time, but it depends on the fractions of sequential accesses. Okay, so as you can see, the performance is good. And then so in this paper, the researchers compared the performance of SFTL with the ideal approaches, that is the most expensive approach, so optimal page level mapping mechanism. But this research shows that the performance is just nearly same. Okay, so system-wide performance. Okay, just compares the system-wide performance. Okay, last time and this side. So SFTL is also the page level mapping mechanism, but for this page level mechanism, so the researchers exploit the spatial locality observed in workload to storage devices. Okay, and then actually the researchers use the popular bitmap based compression to reduce the size of the cached page level mapping information. Okay, this is the main idea, and then this main idea is work effectively. Then so the researchers can implement the page level mapping approach in their SSD. Okay, so I will conclude the address translation research in SSD. So this address translation in SSD is required because of the unique characteristics of flash memory. So it is required for better performance and then also the longer lifetime of flash memory. But we learned about the pros and cons of the two major approaches like page level mapping and block level mapping. Okay, so like the cache structure or like the direct map, the fully associated or set associated caches, then we can apply we can know the pros and cons of these various page mapping algorithms. Okay, so we need to consider the cost. We need to consider the performance and cost. Okay. So actually, so and then when we apply this page level mapping ideas, we need to consider some cost like a capacity of the DRAM and then also response time, considering the erase. So if the erases are frequently required, then the performance can be degraded. So also write amplification. So we need to reduce this write amplification for better performance and so longer lifetime. Okay, so we need to consider these factors. Okay, so this is the conclusion of the address translation research, and then actually the second topic of today's class is the FTL computation in FTL. So before starting the next topic, so let's take a break for 10 minutes, okay? And then I will explain about, I will present some example computation ideas in FTL, okay? So let's take a break for 10 minutes. So can you see my video? So I changed the, oh, sorry. So I changed the shared screen to, it's a PowerPoint slideshow, so I cannot see my face. Okay. So another topic of today's class is what's that? So in FTL, so it can be called the in FTL computation. So actually until now, we learned about the address translation in FTL. So FTL means the flash translation layer in SSD. And then as we learned, this address translation is actually, it's very similar to the virtual address to physical address translation, because in the SSD, the logical block address is translated into the physical page address. So similar to this address translation in virtual memory. But as you know, the virtual memory, so address translation in virtual memory includes the additional information. So we call this additional information as metadata. And then each entry of this address translation mapping table in of virtual memory also includes metadata, so additional metadata. So this additional metadata provides the information of the permission or some read write or some age of the, that means the age of the this address translation. So those additional information is also stored in the this every entry of the address translation in virtual memory. And then FTL is the same. We learned about the address translation in FTL. The FTL table also stores the additional information called the metadata. And using this metadata, the SSD can perform some additional work or some additional functionalities in SSD. So this time I will introduce the two research papers according to this computation in FTL. So actually the main idea of this research work is that FTL is just a data structure. That means this data structure just used for translating logical block address to physical block address. Also, we can use the additional information or additional metadata for some additional functionality in SSDs. So the main idea of this in-storage computation is this is the modified FTL structure. So main idea is that this FTL structure can be enhanced or modified for specific domain applications. For what? For which reason? In order to increase the performance of applications. So, and then we first we'll first learn about the graph SSD. That means the graph semantics aware SSD. So this graph SSD is developed. It's developed for increasing the performance of large graph applications. Okay, and then another approach is the in-storage indexing. So the main with this in-storage indexing, we can reduce the number of accesses to storage devices. So we learned that storage devices are very slow devices compared to main memory. So we need to reduce the number of accesses to storage devices. The problem is that as the data size increases, this number of accesses to storage devices also increases. So that is the problem. So if possible, then we need to reduce this number of accesses to storage. The frequently used idea is also the caching idea. So that means that the the data accessed from the storage devices are cached in the main memory. But we can apply some additional enhanced ideas in the storage devices. It is because, so we learned that until now, we learned that storage devices like SSD learns firmware, okay? And then also SSD supports the address translation. It's which is very similar to address translation in virtual memory. And then the virtual memory is managed by software. So that is the operating system. So that means this address translation is the kind of data structures. So, and then if we can modify the data structures for better performance, some efficient accesses to storage devices, we can increase the performance of overall computer systems. That is the main idea. So So this slide. So that is what I explained about the main idea of the FTL computation. That means that FTL modification for some domain specific applications. Okay, so I already explained that. So this is the existing function of the normal FTL. So it's a flash translation layer. So SST. Actually, this flash translation layer is the software. So that means that SST firmware, which is used for managing flash memory. And then as we learned, this flash translation layer performs the address translation and garbage collection, where leveling. Okay, those are the some management functions for flash memory. So, and the main idea is that this is the software. So we can modify these structures to increase the performance. So how can we increase the performance? If we can reduce the number of accesses to storage devices, then we can increase the performance of applications. It is because storage devices are very slow devices. Okay, let's talk about the graph SSD. So it's a graph SSD means the graph semantics aware SSD, and then this paper was presented in ISCA 2019. So I will introduce this research work. So what is graph? What are graph structures? So graph structures are composed of vertices and edges that connect two vertices. Okay, and then these graph structures are widely used to explain the relationship between two aspects, or the multiple people, or multiple nodes, or some multiple agents in our society. So graph structures are widely used to analyze the relations between people, actually, especially in social network services. Also, we can use these graph structures to analyze the transportation systems or social systems. And then also we can use the graph structures to analyze the molecular structures, or analyze some to develop the new drugs. That means the medicines. Okay, so graph structures are widely used. Then what is the main issues in these graph structures? What are the main issues in these graph structures? So graph structures used for representing relations between two vertices. And in order to represent these relations, graph structures use the very wide connection matrix. And then, as you know, in the social network services, very popular person is connected to very large number of people, but normal people like us is sparsely connected to our neighbors. So that means that the number of connections to the people that is called the followers. So number of followers of our normal people is very small compared to the celebrities. So usually there are many people, there are lots of nodes or lots of vertices in the graph structures, but that means that the size of data is very large. However, the connections in these graph structures are very sparse. So that means that if we just represent these graph structures as the very large matrices, but the most of elements in this matrix usually have zeros, because the nodes, many nodes are not connected to each other. Usually for very normal people, okay, not the celebrities. This is the main issue of the graph structures also. So, but graph structures are very important. So many applications analyze graph structures. So usually in the very large server systems, these graph structures are stored in storage devices, and that's obvious. And then in order to process or analyze these large graph structures, we need to transfer this graph structure data into host DRAM. But the host DRAM is very expensive. So DRAM is more expensive than SSD, and that means that the size of this host DRAM is usually much smaller than the size capacity of storage devices. And then as the size of the graph structure is very large, the entire graphs cannot be stored in this host DRAM. So in order to analyze the graph structures in the server systems or the host system, graph structures are frequently accessed from SSD, and then that's the problem. If graph structures are frequently accessed from storage devices, that means the overall performance of these server systems or computer system will be very low. Okay, that's the problem of large graph applications. Okay, and then another problem is that when we access the storage devices, that means the SSD, then we know that this graph structure, the data in these SSDs are accessed at sector granularity. So that sector is some abstracted block seen by operating system. But as you know, inside of the SSD, the data in SSDs are accessed at page granularity. Okay, but these graph structures are not graph structures does not fit in this page granularity. So graph structures are randomly assigned inside of the pages of SSD. So this page granularity is not friendly to graph structures. That's another problem. And then in order to access the target page inside of the SSD, as we learned, we need to perform the address translation. And so in this paper, the authors refers to this address translation table as the flash translation table, FTT. And then the concept is the same. So logical page number is mapped to the physical page number like this. So in order to access the target page that contains the graph structure, we need to perform the address translation via this flash translation table, and then we need to access the flash memory inside of the SSD. But idea is that the SSD has the DRAM and also the SSD processor, that's the embedded processor. And then, as you know, this embedded processor is a general purpose processor. That means that any programs can be run by these general purpose processors. And then using also the address mapping structure is the software data structure. So that means if we modify this data structure inside of the SSD, then we can efficiently access graph structures stored in SSD. That's the main idea of graph SSD. Okay. So authors also highlight the main features of the graph SSD. So graph SSD use the storage organization in the storage organization, but this mapping information is modified for the efficient accesses of graph structures. And then these graph structures are stored in the flash memory. That means the pages inside of SSD. And then instead of using the flash translation table, that is the page mapping table in the SSD, this graph SSD supports the graph translation using the graph translation table called GTT. So in the flash translation table, the logical page number is just translated into physical page address. But for this translation, the target page is accessed, and then the graph structures are stored in this target page. And then what's the problem? In order to access the target vertices and some connection information for these target vertices, then CPU, the host CPUs need to analyze the data structures inside of these graph structures fetched from the storage devices. So that is some inefficient processing mechanism. So instead of this logical page number to the physical page address, graph SSD just supports the direct translation from vertex ID to target physical page number, the physical page address. So this graph translation table supports the mapping from vertex ID of the graph structures and the target pages inside of SSD. So that is also the main idea of this graph SSD. So what is the main? So this translation table is modified to support the graph structures. And then also, so you know, when the application access the data inside of the storage devices, and then actually we learned that the application access the file system, that is the virtualization of the storage systems. And then when the file systems are accessed, then operating system generate the request to storage devices. And then these requests are based on the sector addresses or page addresses. So in order to support the graph SSD, then these layers should be also modified. So application need to request some target pages inside of the SSD using the new command. Okay. So instead of using sector numbers, we need the vertex IDs to access graph SSD. So that means that the APIs for in order to use the graph SSD, then we need the modified API. Okay, so these APIs are also developed by these researchers. sound animation. So, so this paper also explains the background, the main background of the SST architecture, and then as we already know some basic architecture of the SST. Okay, so yeah, I will skip this page, this slides. Oh, so and then let's talk about the graph representation. So as I explained, so graph size are very large because when we mentioned the social network services such as Facebook or Instagram, so you know that there are the number of users for this Facebook or Instagram is not very large. Okay, so about 10 billion maybe. So that means that each people can be represented as each vertex of graph structures, and then the relations, that means the connections between people can be represented as the edge in graph structures. That means the follower or some friends, maybe is it called the friends? I don't know. So these connections, that means the relations can be represented as the edges of the graph structure. But as I mentioned, but there are lots of people in these social network services. That means that there are lots of vertices in the graph structures of these social network services, but compared to this number of vertices, the connections are very rare, especially for normal people like us. So that means that we can, so this is the example graph structures. So you can find the vertices here, and then edges are connected between vertices. Then you can find the cost of the edges. That is the value of edges. So we can represent these graph structures as the adjacency matrix. So each this rows and columns represent the elements of the rows and columns represent vertices of graph structures, and then if these graph nodes are connected, then we can write some values to the corresponding element in this adjacency matrix. So for example, so in this example, the vertex number 3 is connected to vertex number 4 with the weight of 2. So in order to represent this information, we can just find the vertex number 3 here and the vertex number 4 here, and then we can find the edge value here, the cost of edge. But the number of connections between the vertices are very sparse. That means it's very rare. So most of the large of elements in these adjacent matrices have 0 elements. So that means that the value of elements are usually zeros. So I mean, it is called that, this matrix is very sparse because this matrix has many zeros. Okay. So if we just use the normal matrices structure to represent the graph structures, then this matrix will include the many zeros. That means that data spaces are wasted by many zeros. So we need to avoid this case. So usually we use the compressed format called the CSR, so compressed sparse law. So in this example, so the CSR format is represented using the row pointer and then column indices and then value of the edges. Okay, so Sorry. So this row pointer just stores the some point of the data location. So if we just find this value, so cost between vertex number 3 and then vertex number 4, then we can first find the vertex number 3, and then we just find the adjacent vertices connected to this 3. So as you can see, the low point for this vertex 3 is the 5. So we can just find this pointer location. So it's a 5. So 5 is here. So we can find that, the adjacent matrices are, that is adjacent vertices are 4 and vertex number 4 and 5. So that means the 4 and 5. And then, for this vertex number 3, the adjacent vertices are vertex number 4 and 5. Then these edges has some cost values. The cost values are 2 and 3. So these adjacent vertices are mapped to the edge weight, the cost of the edge with this value array. So in a CSR format, so it's the compressed format of the graph structures. So these CSR formats are composed of row pointer arrays and then column indices and then values of each edge. Okay. So usually we use the CSR formats to represent graph structures because not to reduce the size of graph structure data. Okay. So let's see how these CSR formats of graph structures are stored in SSD. So when these graph structures are stored, we can just store the so this is how the graph structures are assigned to each page of the SSD by graph SSD. Okay. So this is the simplified view. So you can, as you can see, you can find the row pointer here and then adjacent vertices here. So these adjacent vertices are stored to the page of SSD. So 2.5 and 1.5 are stored, and then in order to access identify some row pointer for this adjacent vertices, then we need some additional information like the vertex 1 is start from this 1, then vertex 2 start from 3, and then these adjacent matrices are adjacent vertices and here. So this information is stored in page of SSD. Okay, and then the next connection information is also stored like here, and here. So in this example, this is very popular. Vertex are connected to many other vertices. So the adjacent vertex information of this vertex number 5 is very large. Then it can occupy multiple pages like this. Okay. So these adjacent vertices are accessed from the host systems, and then in order to access the target page, we need the flash translation table (FTT). So this target logical page numbers are translated to the actual physical page number like this. So instead of this, we can, but as I explained, if we use this conventional translation table, then we need to read this page and then analyze the data inside of this page, and then we also need to access some target pages in the application. So instead of this, graph translation table provides how vertex IDs are mapped to the target physical page. So what's the benefit? If an application just look at the vertex ID, then the predefined adjacent vertex informations are read from the SSD, that means the target physical page. Okay, so usually in order to analyze the graph structures, we need the adjacent vertex information or the edge cost to the adjacent vertices. So this information can be directly read from the storage devices. That is the main benefit of the graph SSD. Okay, like here. But what's the problem? The problem is that, so as I explained, the graph structures are very large. That means usually graph structures include many vertices. So if each vertices are mapped to the target page like this, but so usually the page size of the SSD is about 4 kilobyte to 16 kilobyte. So actually the one page of the SSD will include many vertex information. So that means that the adjacent vertex information from many vertices. Okay, so not say not to reduce the size of the graph translation table, we just map the start vertex, use the start vertex ID, and then this start vertex IDs are mapped to the target page number like this. Okay, so actually in this example, the graph translation table shows each entry of the graph GTT shows the vertex IDs like 1.1, 2, but so actual GTT entry has the 1 like here, and then this 1 is mapped to P1, and then 3 is mapped to P2, 5 is mapped to P3, and the 5 is also mapped to P4. Okay, so and then graph SSD also supports the new command, and then this new command can be implemented by modifying the NVMe commands. Okay, so NVMe commands has it's a driver, it's a software driver, so you can modify this NVMe command easily. So graph SSD supports the new NVMe commands such as the get neighbors or get edge weight, like with the argument of vertex IDs. Okay. So in this example, if the vertex ID number 1 is given with the get neighbor command, then this vertex ID is given to the graph translation table, and then we can find the physical page number. So it's the address of the physical pages that contains the adjacent vertex information for this vertex number, vertex ID 1, and then so this is here. So SSD also analyzed these very page-friendly the adjacent vertex structures, and then we can find it's a vertex 1, vertex ID 1 is here, and then it starts from the first 2 byte here. to read this data, the 2 byte or just 2 byte, and then these edge costs are delivered to the host system. Okay, so we can find the several benefits from this mechanism. The first, the target pages are directly accessed. The second benefit of this graph SSD is that only required information, like the edge cost of the adjacent connections for this vertex ID number one. So only the required cost data is delivered to the host system. So how about the conventional system? Conventional system need to read the entire page that contains the information of these graph structures, and then the host system need to analyze the graph structures. Okay, but with the graph SSD, the adjacent vertex informations are aligned inside of the target page, the physical page, and then graph SSD just delivers the required information, not entire information. Okay, so we can reduce the size of transferred data from SSD. Those are main benefits by graph SSD. Okay, some modification. So I also explained about the modification of the graph SSD. But as you can see, if the new edges are added, then we need to also update the target page of the graph SSD. And then, the update to the flash memory is a very cumbersome process. So we cannot update the target page directly. So we need to generate the new page, and then we need to write this new page into the new empty page inside of SSD. That is the cumbersome processes of the SSD. So let us assume that in this example, the new edges are added to vertex number 1. So new edges are added between vertex number 1 and vertex number 7. So we need to insert this data to this target page number 1. So, but the in-place write is not supported by flash memory. So this is buffered in the DRAM of the SSD, and then the structures are modified. And then, so in this example, as the new edges are inserted, then the size of this data structure is larger than the size of a single page. So in this case, these structures are split into the multiple pages, and then these multiple pages are stored to SSD. And then graph translation table is updated, and then the old page is invalidated. But it's also it requires the 2 writes and then 1 erase, one invalidation, actually 1 invalidation. So, and then if the writes are frequently performs, then it will also degrade the performance of the system. So in order to avoid this, then we can just graph SSD just to support the update buffer, and then these update buffers are managed inside of DRAM of SSD. Okay. So it's very similar to the page level mapping management by the FTL or SFTL. Okay. And then also the graph application should be modified to use the graph SSD. So graph API should be also modified. Then so this is the evaluation platform of the graph SSD. So we use the so I also participate in this research. So we use the OpenSSD platform to evaluate the graph SSD. Then this OpenSSD platform equip the Zinc 7000 FPGA, and then Zinc 7000 FPGA includes the dual core ARM processors and then FPGA part. And then the firmwares runs using these ARM cores, and then the low level hardware engine. So that means that the flash controllers or some interconnections or DMA engines are implemented on the FPGA. And then for this graph SSD, the FTL part of the OpenSSDs is modified. Then this table shows the size of the graphs that is used for evaluation of this graph SSD. So we just compare the performance and the number of accesses to SSD. Then we just compare the performance of get neighbors. So that means that if the vertex ID is identified, then just to read the neighbor information, that means that the edge, the connection information like edges, and then the cost of edges are read from the graph structures. Okay. So for these get neighbor functions, the graph SSD shows the 1.85 times higher performance compared to the conventional SSD. So the speed up is very significant. Okay, and then if we just compares the graph GTT size for this the group translation size to the graph SSD, then means that the size of the GTT is about 8 megabyte and then 34 megabyte. Okay. And then if we just compare the NAND page access ratio, so that means that how many NAND pages are accessed for these get neighbor functions, then we can find that it's about the half of the normal accesses. That means that the accesses to the normal SSD, conventional SSDs. Okay. So and then because of the reduced number of accesses to SSD, then graph SSD can increase the performance of graph applications. So we also compares the performance of the normal graph applications. So it's called the random walk. Then we found that the performance can be improved by 1.6 times. Okay. So NAND page access ratio is also reduced, and then when this usage ratio is increased. So when this is efficiently used. So this is the conclusion of the graph SSD, and then as you know, this address translation part. So address translation part of SSD is modified to support graph structures. Okay, why? The graph structures are very inefficient because of each native characteristics, like the many indirect accesses, and then to access the target data. The graph structures are fully analyzed by host CPUs or host processors. So that's the problem. And then for this analysis, for this analysis, the host system requires to access SSD, like storage devices, very frequently. So that's the problem. They need to avoid these frequent accesses. Graph SSD modifies the address translation part, address translation data structure. That means that the target pages are directly accessed by graph vertex IDs, like a graph structure, the native feature of the graph structures. Okay. Okay. So, and then any questions?
교수님 하나 질문해도 될까요?
네.
결과에서 스피드업 부분에서
네.
데이터셋 같은 경우에는 8맥 콜라보레이팅 필터링? 이거 그 8메가 쓰고 베이스라인이 1기가 쓴 게 이제 CSR 때문에 확 줄어든 거고, 근데 이제 스피드업이 1.85배로 나오는데 이게 그 스케일링이 안 좋다고 해야 되나? 이게 줄어든 거에 비해서 스피드업 게인이 그만큼 안 나오는 이유는 그냥 어떻게 봐야 될까요?
그 사이즈가 이렇게 줄어든 게 아니라 그 GTT 사이즈를
네네.
그냥 나타낸 거고요.
네네.
네. 그 베이스라인은 그냥 그 CSR이 적용된 그러니까 CSR 포맷으로 그래프 스트럭처가 SSD에 저장이 돼 있을 때 그거를 말을 하고 있는 거죠.
네.
그렇게 크게 많이 읽을 수 없죠. 그렇게 하면 너무 그게 커지기 때문에 그거랑 비교하면 안 되죠.
네, 감사합니다.
네. So if you do not have any questions, then I will introduce another idea. It's called the in-storage indexing. So actually, this paper is not published yet, but I will just introduce the baseline idea. So index structures are widely used in the database management systems called DBMS. So actually, this is some common example of this database system, database table. So as you can see, you can find the IDs of each entry. Then each entry may have some many items like age, states, or cities, like in this example. So the ID is mapped to a certain customer, and then this table just shows the information of each customer, like the age of the customer, and then where he or she lives, and then the state information, and then city information. Then how can you access so if we just analyze this data in the data, so that means that the data table of the DBMS, then like how many, so for example, how many customers live in California. So for this operation, so if we just have this main customer table, then in order to process this query, such as how many customer live in California. So for this, in order to process this query, then we need to read each entry of this customer table, and then check the state of each customer ID, like here, 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 and then we can accumulate the number of customers. It's very inefficient, because if the table size is very large, then we need to access very large number of entries. So that's very inefficient. And then in order to avoid this inefficiency of the query processing, the data DBMS system, DBMS supports the index structures. So index structures is basically the inverse table of the this customer tables, and then the inverse table is arranged using each item of this customer table entries. So for example, in this index, if this customer table is arranged using states, then this index table has the state ID here, and then this state ID is connected to the customer ID. So if we just find how many customers live in California, then we can just access this index table. This is the inverse table, and then we can easily know which customer live in this California, because this index table is arranged using this key, this item as a state. Okay, so if we just identify the customer ID that lives in California, then we can just selectively access this entry, this entry, this entry, and this entry from customer table. So main benefit of index structure is that we can reduce number of accesses to main data structure. So the idea is that the idea about this in storage indexing means that if we just access the very large database table stored in the storage devices, then this DBMS will require many accesses to storages. But if storage can manage the index structures inside of the SSD, then storage can filtering the queries from host systems. This is the main idea of the in-storage indexing. So, and then also in a new normal DBMS, these index structures are also stored in the storage devices, because this is the data structures. Okay, and then so DBMS also need to access the index structures to identify the target table entry requested by queries. Okay, so the problem is that if the table size is very large, the index structures are also very large. It occupies the largest spaces in the storage devices. And then if the DBMS also access these index structures, then DBMS requires the many accesses to storage devices, and then many accesses result in performance degradation. Okay. So the main idea of this in-storage indexing is that it's the per page indexing maintained in SSD. So we learned about the page level mapping in the SSD, and then we also learned that we do not learn about the metadata inside of this page level mapping table, but usually the metadata is also stored in the this page mapping table, and then the SSD uses this metadata for some more functionality, more functions inside of the SSD. The main idea is that if we can write the indexes that connected to this page mapping information, and when this page mapping table is accessed, actually, for every access to SSD will require the accesses to FTL table. Then while this FTL table is accessed, these per page indexes are also accessed. That means that the per page indexes are also analyzed, and then we can reduce some data transfers between host and storage devices. Okay, so this in SSD index structures are included, and then it's mapped to the page level mapping, and then these indexes are stored as the metadata of this page mapping information. Okay. So let's see how this database table is stored in the SSD. Now, this database table will include the many entries, and then the multiple entries will be stored in each page, or each sector of the storage devices. So actually, the SSD, the basic access granularity is a page. So that means many items, so many entries of the database table will be stored inside of a single page. Okay. And when this page is written to the SSD, and then we know the write operation to the flash memory will take very long time. So when this data is written to the SSD, that means the flash memory, then the SSD can analyze the data of this database table, the entries of this database table. Then we can generate the summarized information that is called the per page indexes, like the range of ages or the state of the customers, like this. Okay, like age ranges or the states where customers live. So these are the summarized information, and then based on this summarized information, we can perform the filtering. Okay. So this is the example code of the TPCH query 6. Then you can find some conditions here. So this is this TPCH query 6. So this is the SQL code. This SQL code identifies the database table here. This is the target database table. And then this is the required filtering operation by this query. Okay. So these are the items, that means the keys of the database tables. And then this is the final computation part. So if you see that this example code, so we can find that, oh, this is the target data stored inside of the SSD, and then many filtering operations are performed by this query for the database systems. And then it's frequent. This is the very frequent operation. Okay. When we analyze the data in the database systems, so we just identify the conditions for that, for the entry of the database table, and then based on these conditions, some database entries are selected from the table, and then from the selected entries, then computations are performed. Okay, so in this query 6 compute to the revenue from the database table. So we can focus on this filtering operation. So if there is no index table, then the database system requires to read entire database table. That means the database DBMS requires to read entire pages that stores this target database table. This is very inefficient. But so if the index is, if there are index structures, and then based on these index structures, we can perform the filtering operation very efficiently. So let's see the example. So this is the query for this index table. That means the query requires the customers in California. Then this is also modified NVMe command. So this is NVMe command is actually the normal NVMe command is the read operation, but this modified command is the read with the indexes, and then the target pages. So this target database table is stored in the LBA1. Okay, so this command is given to the SSD. So if this LBA1 is given, then we need to perform the address translation based on the FTL table, so we can find the PPA. But as you can see, this translation entry is connected to the per page indexes here. So you can see, oh, this page includes customer information, and then the customers live in California. Okay, so this means this page include customer information, and then this customer lives in California. So this page can be delivered, transferred to the host system based on this index information. Okay? But with the same query, the LBA2 is accessed, but if you see that this per page indexes, then CA is not indexed. The state California is not indexed, so that means that this page does not include customer information that lives in California. Okay? So instead of accessing the flash memory, then the SSD just returns the special code. So that means that, oh, this customer information is not found in the target page. And then if the host, and then this page data is not delivered to the host system. So by doing this, we can reduce the number of data, the amount of data transfers from storage to host. Okay. And then, so index can be also updated. So that means that this customer, the customer number 5 moves to California and then Oakland. And then the write operation should be performed inside of the SSD. And then under this write operation, while doing this write operation is performed, the indexes are also updated, and then these updated indexes are stored in the FTL structures. Okay. With this in-storage indexing, the more complicated query processing is called the join processing. So join processing requires the 2 database tables, and then join processing is the query processing that finds the relations between 2 database tables. Okay. So we can also support this join processing by scanning this table, but we can just easily with this in-storage indexing, the join processing can be also stored easily with the per table indexes here. These per table indexes are also managed inside of the SSD. So these ideas are also evaluated using OpenSSD platform, and then so it's a real SSD development platform. Then we just compare the performance using the baseline. That means that baseline means that no index structures are supported, and then host side index. That means that host DBMS just manages the index structures, and then the flex means the in-storage indexing. So that means that SSD also manages the index structures. Okay, so as you can see, the performance is about 2.8 times compared to the baseline, without index. Also, the performance is higher than the host side indexes. Okay, compared to the host side index, the performance is improved by about 20%. Okay. So also compares the performance with the various query processing before the various query processing. Okay. And then also compares the storage IO. So yeah. So conclusion is that the index structures can be managed by storage, and then based on this page level mapping, page level mapping property of inside of the SSD, we can store additional metadata alongside with the page level translation information. Okay, and then if this metadata is provided inside of the SSD, then we can reduce the data transfers from SSD to host systems. And then if we reduce these data transfers, then we can increase the performance. This is the main idea. So in the today's class, I introduced some 2 exemplar research regarding the FTL computation. So as I mentioned, FTL is the software, that is the firmware. Then like the address translation in virtual memory, this address translation or page mapping inside of the FTL is managed by system software. That is the firmware of the SSD. And then we can modify these data structures inside of the FTL for better performance, because the SST may have the more information about some data like graph structures or the data like the database table, then SST can help reduce the amount of data transferred from storage to host system. And then if we can reduce this amount of data transfers from storage to host system, we can increase the performance of systems. So those are the contribution of the modified FTL structures inside of the SST. Okay. Okay. I'll stop here, and then do you have any questions? Okay. So okay. Thank you for your attention. And then let's see you in the next class. Bye, guys.
감사합니다.